Students, good morning. Really, I am so happy to see you once again through this CETEL YouTube channel. Today's session is mass transfer coefficient. We are entering into the new segment in mass transfer. So far, we have been discussed more about molecular diffusion. Molecular diffusion. Molecular diffusion is nothing but movement of an individual molecule through a substance on its molecular scale due to their thermal energy. Moreover, molecular diffusion is the mechanism of mass transfer in fluids at rest and in laminar flow. This is already we discussed a lot. One more information is eddy diffusion. Eddy diffusion, I am already told you, mechanical agitation causes rapid movement of fluids. This rapid movement of fluids creates large masses of fluid chunks, what you call the eddies. Eddies are nothing but characteristic nature of turbulent motion. Each eddies carry dissolved salts within them. This method of mass transfer is called as eddy diffusion or turbulent diffusion. Turbulent diffusion or eddy diffusion is the mechanism of mass transfer in fluids under fully developed turbulent condition. One more important point, turbulence, turbulent region, turbulent motion is nothing but movement of solid particles or suspended particles is in irregular with respect to both direction and time. This is the reason why we are unable to understand the mechanism of flow process involving eddies in turbulent region. Clear? Fortunately, the molecular diffusion is explained by kinetic theory of gases. Using this kinetic theory of gases in molecular diffusion, we start our discussion. We already derived the expression, that is Na is equal to Na divided by Na plus Nb into dAb into C divided by Z into ln Na divided by Na plus Nb minus Ca2 divided by C, Na divided by Na plus Nb minus Ca1 by C. One more fundamental equation, Na is equal to Na plus Nb into Ca divided by C minus dAb into dou Ca divided by dou Z. Clear? This is we already derived equation in molecular diffusion under steady state condition. In this equation, this dAb into C divided by Z is called as local mass transfer coefficient F. The notation is F, local mass transfer coefficient or coefficient in phase interface. Coefficient, mass transfer coefficient at the phase interface, at the phase interface or phase boundary. Listen, already we struggled a lot. Now we are entering into a new segment. What is the necessitation? What kind of struggles we face during turbulent region or turbulent diffusion, turbulent motion? The mechanism of flow process cannot be understood thoroughly because the movement of fluid particles are irregular with respect to time as well as direction. In such a situation, why or what is the necessitation of mass transfer coefficient? The thing is, So far we have been discussed about the mass transfer in single phase system. Now we are entering a two phase system. That is why instead of diffusion coefficient we are entering into a mass transfer coefficient. Mass transfer coefficient at the phase interface or phase boundary. This kinetic theory of gases supports as much as possible, that is dAV into C divided by Z is the local mass transfer coefficient or mass transfer coefficient at the phase boundary. Now I am going to derive the mass transfer coefficient for various cases. We have frequently two cases. One is diffusion of A through non-diffusing B. This is case 1. This is case 1. And case 2, equal molar counter diffusion. This is the two situation we frequently encounter in the mass transfer studies. Clear? Case 1 and case 2. For this case, the base equation is redrafted. For case 1, Na is constant and Nb is equal to 0. Na is constant and Nb equal to 0. This equation becomes Na is equal to minus of dAV divided by Z into dCA or Ca2 minus Ca1. This equation becomes like this. So this can be rearranged. Na is equal to dAV divided by Z into Ca1 minus Ca2. This statement gives an equation, that is flux is equal to coefficient into driving force. This is the base for mass transfer or chemical engineering. For mass flux, it is mass transfer coefficient into concentration difference. For heat transfer, heat transfer coefficient, temperature difference. Clear? In such a situation, now the flux Na is equal to coefficient dAV by Z. This is taken as K, small k suffix C. Small k indicates local mass transfer coefficient. Now the equation is Na is equal to Kc Ca1 minus Ca2. Ca1 minus Ca2 is the concentration difference. Kc is the mass transfer coefficient. Na is the flux. This is the base equation for liquids. I can write like this one. See, this is the individual concentration. Concentration of A at location 1. Concentration of A at location 2. To find the individual concentration, individual divided by total is equal to fraction. Concentration fraction is equal to mole fraction for liquids. Concentration fraction is equal to mole fraction. This is applicable for the case liquids. Clear? So I am going to write this Kc into C, Ca1 divided by C minus Ca2 divided by C. For simplification, I am writing like this. So Kc into C is nothing but KL into XA1 minus XA2. Clear? Na flux Na is equal to this one. So we have two equations for liquids. Na is equal to Kl into XA1 minus XA2. Similarly, Na is equal to Kc into Ca1 minus Ca2. This is in terms of concentration. This is in terms of mole fraction. For gases, Pb is equal to N or T. N by V is nothing but concentration. It is equal to partial pressure of A divided by R into T. Now I am going to substitute Ca1 is equal to Pa1 bar divided by R into T. Similarly, Ca2 is equal to Pa2 bar divided by R into T. Now I am going to substitute this information in this base equation or this base equation for gases. Clear? So Na is equal to Kc into what is the Ca1? Pa1 bar minus divided by RT minus Pa2 bar divided by R into T. So Kc divided by R into T into Pa1 bar minus Pa2 bar. So flux Na is equal to Kc divided by RT. Kc divided by RT is represented in terms of Kg. Kg into Pa1 bar minus Pa2 bar. This is another form of equation to estimate the mass transfer coefficient in gases. Instead of partial pressure, you can use the mole fraction in gases. That means partial pressure of A is equal to total pressure into its vapor phase or gas phase concentration. This is mole fraction of A in vapor phase. This is partial pressure. So Pa1 bar is equal to total pressure into Ya1. Similarly, Pa2 bar is equal to total pressure into Ya2. Now I am going to substitute this information in this equation instead of Pa1 and Pa2. So flux Na is equal to capital K into G. Instead of Pa1, I am going to write P into Ya1 minus Ya2. Kg into P is nothing but Ky into Ya1 minus Ya2. This is the brief information on various forms of mass transfer coefficient for both liquids and vapors. This is applicable for diffusion of A to non-diffusing B. Again, one more case, equal mole of counter diffusion. This will be discussed in the next video. Thank you.